I'd like to welcome you all to this wonderful discussion about torque and tension and fastener testing. My name is Dave Miller. I'll be the presenter here today. And the topic on the screen there is defining the basics of torque and tension and breaking out the factors that determine bolted joint integrity. So what we're going to cover here this afternoon will be the basics of threaded fastener tightening technology, the factors that contribute to joint integrity, some methods of measuring torque, angle, and clamp load, and how frictional characteristics can affect assembly quality and why they are important. So why do we use threaded fasteners? We'll start at the very basics. Why threaded fasteners? Well, they've been in use successfully for centuries. They provide a very convenient means of assembly and disassembly. They're ideal for disassembly, particularly when required for maintenance and repair. And since we're using a lot of new materials to put our products together these days, those materials require advanced processes to maintain and improve quality and reliability. And those processes may include researching our threaded fastener tightening process in more detail to find out what's really happening when we're tightening our new products and equipment. Now, the purpose of a bolted joint is to hold an assembly together with the ability to disassemble the assembly without destroying the components. Pretty simple enough. But the function of the bolted joint goes a little deeper than that. The idea of the function of the bolted joint is to retain a sufficient preload or clamp load in the joint to prevent failure when the assembly is in its working condition. A bolted joint is going to remain tightened when the clamp load generated during the fastener assembly process is greater than the working loads applied to the assembly. The goal is to obtain a clamp load that's greater than the working loads, but note that the goal does not include the word torque. Well, a lot of times we think of bolted joints and tightness as being involved heavily with torque, and it is involved with torque to a certain extent. But to ensure the joint will withstand the working loads, we have to understand the relationship between torque and tension in the fastener and the materials being clamped. Now, to understand a little bit more about working loads, we want to consider the assembly we have pictured there on the screen. The working load might be something like an axial load that would be attempting to pull the two parts that we have here apart. It's simply going to try to pull them apart in an axial direction. The working load might be a compressive load that is pushing the two parts together. It might be a shear load, which is one of the more common applications that bolted joints are used to assemble against. And a shear load is simply where the two parts are being tried to pull together to the side. There may be a bending moment involved where the two parts are sort of being pried apart, one being kind of split up kind of in an angular fashion. Or there may be a combination of any or all of those forces that come into play when we're talking about a working load. So again, we're looking to create enough clamp load that we're going to exceed all of the working loads that are being applied to our part. So that leads us to the question of how tight is right? How tight do the fasteners need to be? Now, tight feels right may work for non-critical fasteners. If you're putting together a small part, or you're putting a curtain rod, hanging a curtain rod on the wall or something like that, that's pretty non-critical. And as you're turning the screw in, tight feels right will probably work for you. But critical assemblies that require significant rework or warranty repair when they fail, may require a more comprehensive tightening strategy. So what is required for joint integrity? When we get asked that question, we can sometimes acquaint the questioner with a diagram such as this one here, which is the famous Ishikawa fishbone diagram. And this diagram attempts to take all of the factors that may influence a bolted joint and break them down in their various pieces. And if you do know all of these factors and you have them under control, you're probably going to have a pretty good assembly. But I usually like to break them down to the 5 things that are most important. Number 1 is clamp load. That is the clamp load that's going to hold the part together. Number 2 is torque. Torque being the energy used to tighten the fastener. Number 3 is the angle of fastener rotation. How far was that fastener displaced? How many times did we turn it, or how many degrees did we turn it? And then the next 2 things that are important are the state of friction and the state of lubrication. They are interrelated, but they definitely can impact what happens and how much clamp load is developed and how much torque we need to apply to reach that clamp load. So let's start with clamp load. Clamp load is probably most important because that's what we really want to measure. That's what we really want to achieve when we tighten our assembly. And clamping load is simply the force that holds the assembly together once the working load is applied. Fastener tension is the stretch of the fastener when it's tightened, and often referred to as preload. Now, a lot of times in the industry, we use clamp load and fastener tension interchangeably. At the time the fastener is originally tightened, the clamp load and the fastener tension are going to be about the same. Once the working load is applied, they may differ somewhat, but they will be the same at the time the fastener is tightened. But they do represent 2 different things, and we want to make sure when we're getting into the details of a bolted joint that we separate the idea of clamping load as the force that holds the assembly together. It's pushing the parts together, if you will. Clamp load is a little different than fastener tension, which is the stretch of the fastener as it's tightened, and that fastener tension creates the clamping load. When the joint is tightened, the fastener stretches like a tension spring, and the parts react like a compression spring. So the parts kind of push back against the fastener that's trying to tighten them, and then the fastener itself is going to stretch like a spring to try and maintain that clamp load. But again, our clamp load we want to have it be greater than the working load. But we have to bear in mind that the clamp load is difficult to measure directly in an assembly. So how can we measure clamp load? Well, we can use something like a load washer. We can place that in under the head of the bolt and tighten it down and measure the clamp load that's achieved. But one thing that we have to account for is the fact that it changes the configuration of the joint. You're adding an additional piece to your stack up. It may be a softer or heavier material than what's already in your bolted joint. So we have to consider that when we're evaluating how that clamp load is measured. You can do things like apply strain gauges to a bolt. These are used fairly common. The downside of this is that it's really for experimental purposes. It's pretty costly in terms of assembly cost, and it does change the properties of the bolt itself, where the bolt has to be machined down, you might have to drill a hole through the center of it, and so forth. So the properties of the bolt will not be necessarily the same as the original part that would be used in your assembly. There's a promising technology using ultrasonic stretch measurement, which is, as I said, very promising. However, it's subject to variation if your fastener has a very short grip length, you've got a long fastener with a small diameter, or there's any kind of bending moment that's brought into play when the fastener is tightened. But there's a lot of research being done, and some advancements are coming along using ultrasonic stretch as a tool for determining clamp load. Of course, you can always use a load cell, but similar to a load washer, it changes the joint characteristics. So it's very impractical to use in an actual assembly. So we turn to torque as a means of determining or understanding how much clamp load we've got. But we have to bear in mind that torque is the amount of assembly applied to the fastener. It's simply a measure of energy, force, applying force at a distance. So we apply 1 pound at 1 foot distance from the fastener, we've got ourselves 1 foot-pound. Torque is typically measured as newtons per meter or millimeters, pounds per inch, pounds per foot, kilograms per centimeter, and so forth. And it can sometimes be used to produce clamp load, but it's not a direct measure of clamp load. Sure, we're applying energy, but not every foot-pound applies the same amount of clamp load as the next. So the amount of torque needed to tighten a joint is going to be highly dependent on the state of friction, and we have to understand that part of it, and we'll get into friction in a little bit. Torque is our most traditional method of verifying joint integrity. It's easy to measure using a torque wrench or a rotary torque transducer. The drawback is the amount of friction under the head and in the threads is what will determine to a great extent how much torquing energy goes into producing clamp load. We always like to use this 50-40-10 breakout to explain how that comes into play, because a small change in your friction can produce a large change in the fastener tension or clamp load. So let me try to explain it this way. Let's say we're going to tighten our joint here to 100 Newton meters. Using the general rule of thumb, 50, 40, and 10, about 50 Newton meters of that energy we apply is going to overcome friction under the head. 40 Newton meters will overcome friction in the threads, leaving us only about 10 Newton meters to actually stretch our bolt. So let's look at kind of a what-if situation. Let's say there's some extra lubrication that's applied to the threads, such that instead of needing 40 Newton meters to overcome the friction in the threads, because of the additional lubrication, we only need 35 Newton meters. So when we apply our 100 Newton meters total, 50 of it is used to overcome friction under the heads. Only 35 is needed to overcome friction in the threads, which leaves us 15% or 15 Newton meters going into stretching our bolt, an increase of 50%. Now, will our fastener system be able to withstand that additional stretch? We'd better hope so. On the other hand, if somehow during the assembly process some additional debris or grit or something comes in under the head of the fastener, so instead of needing 50 Newton meters to tighten our joint, we're going to need 55. So when we apply our 100 Newton meters to the joint, thinking we've tightened it, we've actually had to use 55 of those Newton meters to overcome friction under the head, our 40 Newton meters overcoming friction in the threads, leaving only 5 Newton meters of energy to actually stretch our bolt. And we better hope that having half of that torquing energy going into clamp load is actually going to hold our parts together, give us enough clamp load to overcome the working load. So as you can see, just a seemingly small change in the state of friction under the head or in the threads can produce a wide swing in the amount of fastener tension or clamp load. So for torque to be effective, we have to determine how much of the torque was used to stretch our bolt, produce our clamp load. So for torque to be effective, a certain displacement or angle of turn must have occurred. So when we tighten our joint, we're displacing our fastener, we're rotating it, we're turning it. And what's really fascinating about this is that the amount of turn will relate directly to joint tightness. Angle of rotation is easy to measure with a torque transducer or a wrench that has an angle encoder included in its assembly. So angle then becomes a helpful hand in determining the relationship of torque and tension. Tightening the joint is sort of like pushing the nut up the ramp. If we could take the helix of the coil of the threads off the fastener and kind of peel it out, it's sort of in the shape of a ramp, if you will. And torque is the effort that it takes to turn the fastener, thus pushing the nut up the ramp. Once the parts are seated, fastener rotation is directly proportional to our clamp load, and that's worth repeating. Once our parts are fully seated, the fastener rotation is directly proportional to the clamp load. So angle then becomes a very helpful hand in determining the integrity of our bolted joint, because together, torque and angle measurements can be used to very accurately estimate clamp load. Now, when a bolt is tightened, we usually like to talk about the 4 zones of torque angle. And in this case here, we've taken a fastener to failure, but it allows us to break out the 4 zones that we usually want to look for when we're investigating a bolted joint. Zone number 1 to the left, at the lower left of the graph, is what we call the rundown. And this is just where the extra threads are being taken up. We're not really tightening anything together. We're simply running the fastener in. But at some point, the parts begin to contact. Maybe not fully, but they begin to contact. And that's what we call zone 2, the alignment. And that's where we get that significant little roll up, where the amount of torque that it takes to continue turning the fastener increases. Now, at the end of the zone 2 is a very important point, because that's where what we call elastic clamping begins. Elastic clamping is where we're actually going to start stretching our fastener and producing our clamp load. And it's always an important point to keep in mind that that transition point between alignment and elastic clamping, which is often called something like a snug torque point. We want to make sure that we keep that in mind and we identify that when we're developing a tightening strategy. So we'll continue adding torque to our fastener system up until the point that something begins to yield. Either the threads begin to strip, the bolt begins to stretch beyond its elastic capabilities, or the parts themselves become compressed beyond their elastic point, becoming crushed in some way. And that's what we call our zone 4 or post-yield. Eventually we reach the ultimate strength at the peak of the curve, and then we go into a real yield point where eventually the fastener is going to fail. So these are the four zones, and typically for assembly we're going to want to look at elastic clamping. But it's always important to know what the onset of elastic clamping is, where that occurs, and then also where the post-yield or the post-yield zone begins. So to kind of summarize our basics here on torque, angle, and clamp, torque is the energy required to turn the fastener. Angle of rotation, or angle is the rotation of the fastener. Clamp load is what's going to hold our assembly together. And torque, the torque needed to reach clamp load, is going to be subject to variations in friction. But within the elastic clamping region, angle is proportional to our clamp load. Now, friction impacts it all because friction is the resistance to movement between two opposing and contacting surfaces based on the area of contact, surface pressure, and the energy required for movement. For a bolted joint, the area is going to be the bearing surface and thread contact. Surface pressure is going to be our clamp load, and the energy for movement is going to be our torque. So knowing the state of friction in the joint helps determine joint integrity. Too little friction or too much lubrication, and you end up with over-tightened or broken fasteners and crushed parts. Too much friction or too little lubrication will produce loose fasteners. So what are sources of friction? You might have macro effects, things like the drawing together of the mating threads, bending together of mating parts. The fastener bending is the result of non-parallelism of the bearing surfaces. Or they may be micro effects, such as contact stress deflections caused by the plating, or surface roughness, or thread deformations. Even the type, amount, condition, and temperature of the lubricant can affect it. Here's an example of a bolted joint, the same materials. The only thing that's different is that the low friction graph used suitable lubrication in the threads and under the head, whereas the high friction graph was drawn on an assembly that had a bolt that had insufficient lubrication. So we tighten it to the same point, in this case about 60 foot-pounds, and you notice the low friction assembly achieved about 7,200 pounds of clamp load. But take away all of that lubrication, and we got a little over 2,100 pounds of clamp load, nearly a third of the expected clamp load. So this tries to convey to you how we have to understand what the friction is in our joint. We can kind of demonstrate it in a way simply by looking at the basic torque tension coefficient, where we look at an assembly. We're going to tighten it to 35 Newton meters. It's a 10 millimeter bolt, and we're going to assume a K-factor of 0.13. So when we work this through the equation, we see that we should be getting about 26.9 kilonewtons, almost 27 kilonewtons. If we assume a higher K-factor, you'll notice that as we work our way through, we could expect only 23 kilonewtons, 23 1/3 kilonewtons of clamp load. If the K-factor is even higher, we'll end up with about 20.5 kilonewtons of clamp load, which turns out to be a clamp load difference of about 30%. So you can start to see how a change in the state of friction, as recorded in terms of the K-factor, how that can be important. Now there's reference friction, which is kind of a step up. Reference friction being kind of a total estimate of the state of friction in the threads and under the head. And as you can see, this takes the K-factor one step further because it's taking under consideration the contact area in the joint. It's useful for a comparison of different frictional conditions on bolted joints, and it's based on the assumption that all of the coefficients are about the same. Now, breaking out head friction and thread friction can show the equivalency of those friction coefficients. And there are methods that can be used to determine this. The measurements would be the total applied torque using a rotary torque transducer, measuring thread torque using a torque tension load cell, and the fastener geometry. There are calculations that can be made based on that information determined by those measurements. So you would have, for underhead torque, you would be measuring your input torque and your thread torque. Input torque is made up of thread torque plus underhead torque. So if we look at our total input torque, subtract our thread torque, and that gives us our underhead friction torque. So we can go ahead and do a calculation and determine what our underhead friction torque would be. For our head friction coefficient, we might use a formula that looks something like this. Using our measured and calculated values, we can then calculate a head friction coefficient. Now for thread friction torque comes from determining our thread torque, measuring it, and we know that our thread torque is a combination of thread friction torque and pitch torque. Pitch torque is the amount of that torquing energy that goes into producing clamp load and is calculated using the formula here. Pitch torque is pitch times clamp over 2 pi. Pretty easy. And it comes out to typically around 10 to 20%, usually closer to 10% of our total amount of applied torque. So we do the calculation where we calculate the pitch torque, subtract it from thread torque, and that gives us our thread friction torque, which we can then put into the formula and determine what our thread friction coefficient is. It's all pretty straightforward. Just take measurements, do some calculations, and then we can put our thread friction torque into the coefficient formula and determine what our thread friction coefficient would be. In this case here, you can see these are simplified formulas that we're displaying here, but you can see it's not rocket science. They're pretty basic concepts. The coefficients that you see there, the 0.159 and 0.578, are geometric coefficients based on the threaded fastener. This might be an example of a standard friction coefficient report where 10 samples were run and coefficients of friction were developed for the threaded area, the head, and reference friction, as well as displaying some of the measured values that were recorded during the tests. And of course, a lot of customers will want to look at the mean values, particularly for the coefficients, and what kind of range there is, the high and the low. So a K-factor report may look something like this, where the K-factor is recorded and calculated throughout the test. Most often they're displayed versus a clamp load. So we can see here in this particular test, our K-factor was calculated to be 0.19. It defines the relationship of torque versus tension in the joint, but there's no indication of where friction lies. You can take a look at friction torque measurements, where we're looking at the total input torque, the amount of thread torque, and the amount of underhead torque. So we can see here the total amount of torque that we applied. We can see that our underhead friction torque was about 19 Newton meters. Our head friction torque was about 27, or our thread friction was about 27 Newton meters, and our actual pitch torque was about 7. Meaning basically 87% of our input torque overcame friction, only 13% went into clamp load. Now we're going to look at our thread coefficients. We can graph them, take a look at it, and we'll see that our thread friction was about 0.2. Our reference or total friction was about 0.16. And our head friction was about 0.11. This would indicate, in this case here, that there was some kind of additional lubrication perhaps under the head of the fastener, or that there was some additional friction present in the threads, such as use of a prevailing torque lock nut or something on that nature. So this is one of the ways that we can look at friction coefficients. In this case here, the higher thread friction coefficient, lower underhead friction coefficient would indicate that there was something in that particular joint that influenced those values, whether it was physical in terms of the mating of the bolt and the nut, or the state of lubrication. And typically, your reference or total friction is always going to be somewhere in between the two. I'd like to take the opportunity to thank everyone for taking some time on their busy afternoon. Appreciate you listening in. I'd like to thank you all and wish you all a very good afternoon.